Okay, we're going to think back to what we discussed earlier in the notes about symmetric functions or symmetry, odd and even, and we're going to apply that to functions now. And so while there's a lot of functions that are neither even nor odd, our concern is to be able to do two things. Either identify a graph that is odd or even, and remember that odd means that we have symmetry to the origin, or a graph that is even, which means we have symmetry to the y-axis. Now, the second thing we want to be able to do is prove that a function is odd or even, and that has to be done algebraically. You cannot do it using a graph or a table. And so, just as a reminder, if a function is even, that means we've got y-axis symmetry, which means that f of negative x is equal to f of positive x. And if a function is odd, that means we've got origin symmetry, which means that we've got f of negative x equal to the opposite of f of x. And so what we're going to do here to prove if a function is odd, even, or neither is we're going to substitute negative x in for x, and if we end up with the exact same thing, that's going to be even. So if we end up with the exact same function, that function is going to be even. If we end up with the opposite of the original function, that is going to be odd. So exactly the same as even, opposite is odd, and if neither of those things happen, then the function is neither odd nor even. Okay, so if we look at letter A, we have f of x is equal to 5x squared plus 5, and so I'm going to start by substituting in negative x for x, and so this is going to say 5 times negative x squared plus 5. Now, what happens when I square a negative? The negative ends up going away, and I just end up with positive x squared. So this becomes 5x squared plus 5, which is exactly the same as the function that we started with. And so therefore, since we substituted negative x and ended up with this exact same function, we call this function even. Okay, letter B, we're going to do the same thing. We're going to substitute negative x in for x. This is going to be negative x squared plus 8 times negative x plus 12, and then simplify. So negative x quantity squared, again, just goes back to positive and becomes x squared. 8 times negative x becomes negative 8x, and then plus 12. And is this the exact same function that we started with? No. Is it the exact opposite, or just the opposite of the function that we started with? Well, that would be negative x squared minus 8x minus 12. That's not the opposite, what we ended up with. And so therefore, since it's not exactly the same, it's not the opposite, we say that this function is neither even nor odd. Okay, and then finally, letter C, we've got h of x is equal to 5x cubed minus x. So again, same idea here. We're going to substitute in negative x for x. So 5 times negative x cubed minus negative x. And so what happens when I cube a negative? Well, it's going to stay negative. And so this is going to equal, when I simplify, negative 5x cubed, and then minus negative x becomes plus x. And what I notice is that that is the opposite of the function that I started with. So this is equal to the opposite of h of x, and since h of negative x equals negative h of x, we say that this function is odd. Okay, next thing we're going to discuss are vertical asymptotes. We're going to talk more about these later on in the semester, but I want to give you a little preview here. And so if you'll take your calculator and just graph the function f of x is equal to 1 over x plus 3, I'd like for you to figure out what happens there at x is equal to negative 3. And so hopefully you see that the graph is showing you a vertical asymptote at x equals negative 3. And so why is that? Well, here's one reason why, is because if we evaluate this function at negative 3, remember we're going to get 1 over negative 3 plus 3, which is equal to 1 over 0, which we say is undefined because we cannot divide by 0. So because I'm getting undefined, that is a good indicator that this is a vertical asymptote, and notice that -3 is a value that makes the denominator 0. So back when we talked about domain earlier in this lecture, -3 would have been a restriction because that denominator cannot equal to 0, and so that's why we end up with a vertical asymptote at x equals -3. Now, if you graph the second function, x squared minus 9 over x plus 3, what happens at -3? Well, hopefully when you graph this, what you're seeing is something maybe similar to this. Let me see if I can do this correctly. Here we go. And then at 3, you're kind of seeing like this missing pixel, especially if you zoom in. And so what that's called is a removable discontinuity. And we talked about that earlier when we discussed continuity, is that this is removable discontinuity because it's just one point missing, and we sometimes call that a hole. Now, how could we have known that without graphing? Well, if we evaluate g of -3, what is that going to give us? Well, if we plug it in for x, we're going to get -3 squared, subtract 9, divided by -3 plus 3. In the numerator, -3 squared is 9, minus 9 is 0. And in the denominator, we also get 0. And this 0 over 0 is what we call an indeterminate form. Indeterminate form. It means we don't know what's going on at x is equal to -3. And so we have to do a little bit more of an investigation. And so g of x is equal to, what I'm going to do is I'm going to factor that numerator of the original, and it factors as a difference of squares, x plus 3 times x minus 3 over x plus 3. And what you notice then is that x plus 3 cancels out. And so this is equal to, in that case, x minus 3. Now, it's not exactly equal to x minus 3 because we've got to add in this restriction that x cannot equal to -3. But other than that, the graphs are exactly the same. And so how do I know if there's going to be a hole or a removable discontinuity? Well, if you plug a point into your function and you get 0 over 0, you should look for a removable discontinuity. Otherwise, a vertical asymptote is going to occur in a rational function whenever that denominator is equal to 0. Okay, finally in section 1.2, we're going to discuss end behavior, and end behavior goes along with horizontal asymptotes. So we just discussed vertical asymptotes, now we're going to talk about horizontal asymptotes, and there is a very straightforward way of finding a horizontal asymptote. It's going to be using these guidelines here, and I'm going to give you a nice acronym that should help you keep this information organized. Okay, so number 1, if the exponent is larger or bigger on bottom, the horizontal asymptote is the horizontal line, y is equal to 0. And that can be summarized with a 4-letter acronym, BOBO, which stands for bigger on bottom, 0. So the O is not really an O, it's really a 0, bigger on bottom, 0. But make sure that when you write that answer, that you put y is equal to 0, since these are equations of lines. Okay, number 2, if the exponent is larger on top, then there is no horizontal asymptote, and so the way that we abbreviate that is with the 4-letter abbreviation BOTN, or BOTN, which stands for bigger on top, none, meaning there's no horizontal asymptote if the exponent is larger on top. And we're talking about the biggest exponent, not just any random exponent, but whatever the largest exponent or the degree of the numerator and denominator are. If that degree is bigger on top for number 2, we say that there is no horizontal asymptote. If the degrees or the exponents are the same, we divide the coefficients to get the horizontal asymptote. So the way that we abbreviate that is EATS, which stands for exponents are the same, DC, divide coefficients. So altogether, BOBO, BOTN, EATS DC stands for bigger on bottom, y equals 0, bigger on top, none or no horizontal asymptote, and EATS DC, exponents are the same, divide coefficients. Okay, so I'm going to show you how to find the horizontal asymptote And then what we want to be able to do for calculus is write a limit statement that describes the end behavior. So I'm going to give you your first taste of what that looks like. Okay, letter A, we have f of x is equal to 4x divided by 2x squared plus 1. And so this is a rational function, which means it's a fraction. We have a polynomial in the numerator, a polynomial in the denominator, and we are looking to see where is the biggest exponent. And the largest exponent in this rational function is on bottom. And so what that means is that we fall into the first category, which says bigger on bottom, 0, and therefore what that means is that the horizontal asymptote is y is equal to 0. Now, how do I write that as a limit statement? You did this in Algebra 2 in what we would call like function notation, but we want to learn how to do it in limit notation. So here's what we do. We write LIM, which stands for limit. Underneath that, we're going to put x goes to positive and negative infinity of the function, which in this case is called f of x, and this is going to equal to that value that you got for your horizontal asymptote, which in this case is 0. Okay, letter B, we have g of x is 4x squared over 3x squared plus x plus 1. Now notice here that the exponents are the same. We have an x squared and an x squared in both the top and the bottom. So this is going to fall into that third category of eats DC, which means that in order to find the horizontal asymptote, we're going to say that it's y equals the ratio of the coefficients. So those coefficients in the numerator is a 4, and in the denominator is a 3. And so our horizontal asymptote is the line y is equal to 4/3. To write that as a limit, we're going to say the limit as x approaches positive and negative infinity of the function, which this time is called g of x, is equal to 4/3. Okay, finally letter C, we have 4x cubed in the numerator, a 2x squared in the denominator. And really and truthfully, the only thing that matters is that lead term. Don't worry so much about anything else. Just look at that biggest term. In the numerator, it's an x to the third. In the denominator, it's an x squared. That's what you're looking for when you determine if it's Bobo, Botan, or eats DC. So in this case, the biggest exponent is on top, and so this falls into the Botan category, which means there is no horizontal asymptote. And so the way that we would write that as a limit statement is that the limit as x approaches positive or negative infinity of h of x is equal to infinity. And when we write that statement, it doesn't mean that that limit exists. In fact, it says the opposite of that. It says that the limit does not exist because of there not being a horizontal asymptote. Or another way to say that is unbounded behavior. But I'm getting a little bit ahead of myself. We'll talk more about that when we get to calculus. For now, you just need to know the skill of writing this as a limit.